Antiderivatives seek to reverse differentiation. So when I have a function, say 3x to the fourth plus 2, and I take its derivative, I use the different differentiation rules to figure out what that is. I'll get 12x to the third, and this 2 would disappear. If I seek to undo it, I basically use the same rules that I would use for differentiation, but reverse the order. So for a function like this, something simple like this, I reverse the power rule. I would get, and I don't have the notation for differentiation yet because I don't know about integration yet. But in the future there will be specific notation for antiderivatives. But for now, just forget about the notation, and I'm going to get x to the third. But also when I differentiate this, I have to bring this down to multiply it. So I need to divide it by 3 to undo that. And this would be the solution. But it's not only that, it has to be plus c, because when I differentiate, all the constants are lost. When I undo the differentiation, the only information that I cannot get back are the constants. Or if I want to do another level of anti-differentiation, let's say I were to do another antiderivative. Let's say I had f double prime, and I wanted to figure out what just f of x was. Then I would have to do another antiderivative. So this would be equal to, and this would be x to the fourth now, and then I would be divided by 12, plus I would have cx now plus d, because this term would have been eliminated as well after being differentiated twice. So those are just the beginning steps for what is going to be called integration. That's what taking the antiderivative is. We're going to be integrating and figuring out what the antiderivative is, and they all are pretty simple. Something like cosine x. If I take the antiderivative of this, I'll get sine x plus c. And all of them are going to have this constant value. If I want to figure out what this constant value is, I can, but what I'll need is an x and a y. So if someone gives me a 0.12, then I can say 2 is equal to sine of 1 plus c. And then I can figure out whatever the difference is. I can just solve for c. So that's how I would figure out what the constant is. And these are useful because a lot of times I will be able to know or measure the rate, or let's say the velocity or the acceleration, and then I'll want to be able to get an equation for it. A lot of equations in chemistry and physics are based off of measuring the rates and then integrating or going backwards, doing the antiderivatives, and then getting an equation for the position or whatever they're looking for when they are reverse doing the derivative of these different functions. If it's speed, you'll get position. If it's, let's say there's a leaking tank or something like this, it's leaking water out, they might be able to measure the rate, like in oil spills or something like that. They might know what the rate was, and from that rate they'll often be able to figure out how much total of this oil is spilled out of like a hole in the ground where you don't know the total in there, so you can't just say, well, how much is missing. So that's the idea of a lot of these, some ideas for uses of anti-differentiation.